what would happen if we said broadcast send and broadcast receive? Is there any additional complication versus just send and receive?
It's essentially the same thing. The sender is, the root is basically sending the message and the others are receiving. So it's basically just the same as send and receive. B cards receive and B. Because the receiver, because he's calling broadcast and he knows the root is 0. So he knows that root 0 would send me.
No, that's right now.
Yes, sir. So instead of broadcast, he can call receive.
So in bcast receive, now we have the ability to say I want to receive from anybody who's broadcasting in my group. Right? Which we couldn't have done by simply saying broadcast, because there has to be an asymmetric send and receive.
Problem here that specific bcast send will be that it will become too rigid, and will fix up in the code itself that this thread will be sending. But
no. Bcast send doesn't have to say anything. Right? It's like a send. I said bcast send. I don't have to specify a receiver. Right? I just say this is the buffer. This is the size.
If by that the value of root can be determined at the runtime, so that the thread which is actually sending data can vary depending on the conditions. But if you fix that in the code, that and bcast send in that way, then that thread will be sending to the data to
That can also be.
That is more so in the current scheme, right? You say bcast, then I know that I am going to receive broadcast from number 3.
So otherwise also you can do it.
But that can be determined at runtime.
Actually, here also you can.
No. Those two are exactly the same.
So if there are multiple broadcasts from 2 different threads, and there will be then 2 B receives for some thread, then both of these could be matched to a single broadcast and only one of.
So the level of synchrony will go down, right? Okay. That's a design decision to make.
Yeah, the same.
Now, when we say we are allowing to receive from multiple sources, receive broadcast from multiple sources, that means potentially I can be broadcasting. Right? More than one member in the group will be broadcasting, so that somebody can receive from him and him. So now look at it from my point of view. Somebody has broadcast, which I should be receiving, and I also have to broadcast, which everybody should be receiving. Should I do broadcast receive for him first, or my broadcast send first, or does it matter? Because when I say broadcast send, that better match with that guy's broadcast receive.
But this is the same as this example. I mean, you have to choose whether you call 0 first or 2 first.
It is a little different.
But all these problems are because of the synchronous, like blocking nature of the call. But why does it have to be blocking in the first place?
No, it doesn't have to be blocking, but the fact that there is a level of order that it gives to you, right, is useful. So that
Synchronization issue, right? It's a design issue. That's like a programmer's problem, not the system's problem.
right. So you can basically raise more and more problems to the programmer, and at some point people will stop using it.
This problem looks to be the same as the standard deadlock problem.
It is. So basically, you are almost guaranteeing a deadlock. Right? He has a send and receive, and I cannot have a send and receive.
But this gets solved if you have a non-blocking issue.
This can get solved if you have non-blocking issue and you allow to reorder some things. However, if you do have some level of synchrony that you expect from broadcast, then it does not quite make sense from the user's point of view to have multiple people broadcasting and you ready to accept from anybody. Right? Because there will have to be an order imposed. Because I am receiving that same broadcast, I have to receive that before I send mine. So that order being imposed essentially says, you do your broadcast, then I do my broadcast. And then everybody knows that his broadcast comes before my broadcast. So there is no select involved.
So the same happening both when you're doing a send and receive.
In send and receive, you don't have to be receiving the same thing that you're sending, that the other fellow is sending. Some third fellow can be comparing your send and his send and deciding to choose one of them. Right? Here, you must order yourself with that send also, because you have to receive that send.
One of the sends.
You have all the sends because it's a broadcast. That other fellows send, you have to receive because you are also part of the group.
If you have multiple things being sent to you, you have to choose one.
This is not even that. This is that there is a third recipient who is ready to receive both of us and it does a select. But between the two of us, it has to be guaranteed that either he sends first or my broadcast happens first. The programmer knows that. And if the programmer knows it, why would the programmer select? It will always say broadcast from that route first, broadcast from this route next.
So are we saying that we do not need this as a feature?
Yes.
I thought we were discussing what is the problem if we have this feature.
That is the problem, that you can't use this feature if you have this feature. Okay.
What about blocking? I guess I think the block. Why is this a blocking call and not non-blocking? You said that
why is this a non-blocking call? It could have been a non-blocking call. It's just reducing the level of synchrony that you get a little.
But there is no issue with the.
No, it can be implemented with non-blocking. In fact, that may happen in one of the MPIs in the future. Gather. So the same issues now apply with all. We're not going to rediscuss the issues. For all group communication, sorry?
You will not be able to use the issue.
The issue being that you basically want a common primitive that everybody calls that gets matched with each other with the similar type of parameters that broadcast had. Okay. And so you will see the so some of these, for example, when you are broadcasting, you're simply saying, send this piece of data everywhere. When you are gathering, then you're saying, send this piece of data and that it gets filled in these places. So there is more information to be provided. But beyond that, the same parameters are going to remain. Right? For example, in MPI gather, there is a send buff and a receive buff. Right? Send is what is being sent and gathered at the recipient. Receive buff is only for the recipient. Right? So everybody is sending. It's kind of the opposite of broadcast. Right? Everybody is sending and one is receiving. The send buff must have some value for everybody. The receive buff can even be null at the non-gatherers. At the gatherer, it has to have enough space to keep everybody's data. Right? Why is send not? It's not doubling as receive. In broadcast, there was only one buffer.
Also, the one who is gathering
needs to have much more information, much more space, right? Because you're getting that many copies of send. So that's why there is a separate need for a
That
receive
is
buffer.
opposite of scatter, not broadcast.
It is opposite of scatter, but because we are coming from broadcast right now,
So it is also called by every thread.
it will also be called by every thread. Every thread will agree that this is the root, meaning this is where the gathering is happening. And then there is a
The
communication.
receive count has to be constant for all. So
No. Receive buff, receive count, and receive type can be junk at everybody except the root.
So the thing is that if the root says receive count is 100, so it only gathers 100 elements from each thread, from each process.
Now, it will match only if receiver is ready to receive enough, because the buffering is not being provided, or it's not going to keep the data in the buffer so that somebody else may read that later on. Okay, so just like in broadcast, you have to know how much data you're receiving. Here also the root has to know how much data it is receiving. And that means that the root send is important, because root is also a sender, one of the senders. The call that root makes on its send side, meaning the send buff, send count, and send type, doesn't have to be the same as all the other members of the group. What does have to be the same, in fact, buffer will not be same, it's a local pointer. What does have to be the same is the size times the type size. The total amount of information being sent by everybody has to be the same.
That was the thing, that if I divide means data into multiple processors in MPI and they are of unequal sizes, then I can't gather.
You can't gather. But there is something at the bottom of the slide you can do. There is a gather V, where you can gather different amounts of data from different senders. Okay, but the default gather, everybody has to send the same amount. It can be called a different type, it can have a different count, but must add up to the same thing. And the receive type and count has to match with it. Okay, and so I'm going to show you an example.
Is it not an issue? The receive type can be arbitrary, because if you're sending integers and it sends them as a cart, then you mess up the little and the beginning.
No, because when you build the type, you're building it from the primitive types.
Yeah, so if I have an integer,
it knows that it is sending you MPI char, and you're getting it in MPI int, right? So it is going to collect, well, it is not going to interpret the int for you. So in fact, in that example, you may have trouble. When you say 4 MPI chars and that guy expects 1 MPI int. Okay. However, if it is a primitive, you have built a struct or an array based on primitives. And so this guy said, I'm sending you 100 ints. And you say, I'm getting a struct which has 100 int fields. Because you have built this, that is going to work fine. Okay. And all gather is a version where root is not specified, because everybody is the root. Everybody still has to make the call, which is going to match. But the data is going to be collected at everybody, so everybody must have enough receive also. In that case, the receive parameters become important. Okay, here is the example.
Just compare the performance. So if I, instead of gather, I call a for loop and I receive from everyone. So is it similar in performance, or gather is more efficient?
you will optimize gather.
The idea for these functions is primarily optimization. Okay, there is a slight bit of synchrony that it gives you because of the non-blocking nature of it. So you have to actually compare it realistically with the non-blocking send and receive. in which case this is supposed to be faster. With non-blocking send and receive, you don't know. Right? It depends on whether that non-blocking thing allowed you to do something else.
So, I mean, we know the library, like we saw various architectures that processors can be arranged in. Like, okay, so over there, like a gather would optimize that you want to send
Yes.
shortest path.
Yes. Yes. In fact, nowadays the major installations are on just Ethernet type networks, but people still have cube and tree type networks, and people do implement MPI on those networks because those networks are specially constructed for high performance. They're optimized, gather and all group communications are optimized there. Okay, so the top 4 lines here are just declarations. So you've declared a communicator. You have, in fact, it might as well have been the WorldCom. You get the size of the communicator so that you can allocate enough space to hold every member's result. You create an array type. Right? So MPI type contiguous creates an array, a type which is an array of 100 MPI ints. Okay, and then you commit the type. If you recall, we discussed that. And the receive buffer is going to be made of enough size to hold G size, the membership of the group. Okay, so there's going to be some amount of data coming from everybody times 100, because 100 ints are coming from everybody, and size of int. Okay, so you allocated that much space. And now in the MPI gather call, in receive buff, right? Send buff we're not talking about. Send array is just array of 100 ints. In receive buff, you say I'm going to be receiving one data element of R type. That means I'm going to be receiving one data element of R type from every member of the group. Okay, and then the root. Everybody has to agree on the root. This is the root, because other people don't need to allocate that receive buffer. And so that's what it is. Any questions?
So there won't be any inconsistency in MPI internet. Can there be?
In MPI, int and the int array. No, in this case, this is guaranteed to work perfectly.
MPI int can be accessed as an
MPI int is not a type.
just a placeholder.
MPI int is actually a constant. Okay, it is a constant type for internally. So it is not C type, I should say. It's not a C type. It is an MPI type struct has been defined, which says something about how this type has been built, and that is, those fields really are used only for when you build the type, and when for the default types all those fields are not used. Right? It just internally says this is this type, and so you don't cast from MPI type to C type ever.
The gather call will be same at both the root and the non-root, the way I call it.
So for the non-roots, just to complete that, there would be a send array allocated. It will be filled with 100 integers, and that's it. The call will look basically the same, with receive buff potentially null, and those other two parameters, whatever you care. Nobody needs to know.
So what is one mean?
Huh?
Receive buff one.
One element of R type. Okay, from every member.
This one, if we can get multiple copies from each member.
Multiple copies of what?
Two, that means he's going to get 2 copies of R.
2 copies of R type from every member. Yes, which could have been done. It would just have been matched with a send of 200 ints.
Sir, why is the commit there actually?
Why is what?
The commit, why is the syntax being included in syntax? Committing a particular type.
Committing. Because you can build type incrementally. So there is, for every type you build, there is a commit call that.
Why is it? I mean, this is a syntax overhead.
Syntax overhead.
In this, you are given a, when you create a type, automatically it should be figuring out.
You shouldn't need. You shouldn't need commit. You are saying. In some cases that is true, but internally it has to basically set enough resources to make sure that it doesn't need any more information for this particular type.
But it can figure out from the type continuous.
In this case, right? In this case, because you don't have any more to do, you're basically saying this R type is done. It is only an array of 100 things and nothing more. Okay, you could edit R type.
It will be changing R type.
Yeah.
But it won't change the type that it created.
If you have committed.
If I commit, whatever it was at that point, it.
Right. It basically takes the snapshot. Reduce is similar. By the way, in gather there is also a notion of in place, where for the recipient there is no send. Okay, so you physically put your data in the correct slot in the receive buffer, and so you don't have to allocate a send, and everybody else's data just comes and lands at the appropriate slot. Okay, it's just a minor optimization.
And it's ordered, means it would be filled in order 0, 1 rank.
Yes, by rank. Yeah. MPI reduce, similar. Group communication, which will have the similar kind of parameters. At the end, everybody will agree where it is being reduced. The communicator, of course, has to be there. You'll have to provide what is it that you're reducing, where is the result going to be, and the reduction type.
So regarding the commit, I mean, is it so you don't have to create multiple parameters and you just use one parameter, create a type, commit it, again create, give a different definition, again commit it. Is that how it is?
Not necessarily. You do some things to the type and then you commit it. Right? So instead of it keeping track that let's figure out what you've done in the last moment, it is going to make a copy in its internal memory about whatever this data type consists of, and then you can do whatever you want with it. Right? At that point, you don't have to ensure that this data type is going to remain consistent.
Why is it changing it so fast? Why would the program write that? You actually know the structure, you do your definition, that's it. Why would you do multiple definitions?
Because you can incrementally build things into it.
And if you change until now, then what definition you will use in the following code? You committed it once, but under what name?
I think it would be undefined if you did that without committing. I should verify, but that's what my guess is. That if you make some change to it and commit and do not commit, there may be some hanging things which are not properly set.
One easy thing would have been that continuous would have contained the commit call as well.
But maybe
Yeah.
that call
That is also
is just allocating memory. It's not creating data. Might be possible that that call just allocates this much space to any variable that you give.
No, somebody has to keep track of what all you're adding into this type, right? And it is we can. It's an open source, so we can take a look at what OpenMPI is doing. It is probably using this R type as a pointer into something, right? Where things are being modified, and once you commit, it knows that that piece of information is fine. Now you start modifying R type. Then either it's modifying that piece of information without actually keeping it in a consistent state, in which case something wrong may happen, or R type is a type which has enough fields to store everything about this type. Okay, I suspect that can never be, because R type is an incrementally being constructed. So when you declare R type, you don't know what kind of struct it has, right? So you wouldn't have defined in MPI type, MPI data type, this is a struct which has a field size, which is a field this and the field that. Okay, you need to actually store some piece of information that can be later interpreted dynamically. And so it wouldn't, if you could do that you could say this is an MPI type whose struct says that it has 100 fields, 100 ints. If you could do that, which you couldn't, then it wouldn't need a commit, right? But you can't, so it's going to have to keep some piece of information, and because it's being interpreted dynamically, there has to be some consistency within it, which is probably what it is setting up at the commit time. Okay.
I think you have to build, when you need to build structs, you do it in multiple calls and then commit.
No, so the question is, why wouldn't you be able to simply say...
Because you don't know when your struct is complete, you can follow it by char, by float, so you have to do it over multiple calls. And
No. That doesn't answer the question for the following reason. I keep adding things to this struct, that is MPI, or to this type, which is MPI, which is of type MPI type, MPI data type. And whenever I call, whatever I've added to it is what I mean. Right? What is the need for commit? And I suspect it is because MPI type itself cannot store all the pieces of information, because it's a dynamically changing, you're constructing it incrementally. So that piece of information is stored somewhere, and it has to be in a consistent state. It's not internally. So if you looked at MPI type, MPI data type, it wouldn't be a type def with these specific fields which have all the information about the type you're going to build. Couldn't be, because you don't know what type you're going to build. If that were the case, then it would be enough to simply modify the type, because it's right there, and call with that given R type, okay, in this example.
So once I commit, I can't do any changes to the type.
That's what is supposed to be.
Changing the structure, how will it know how to allocate it for directly to the parts, to two different parts of the structure? This change here and then some other change. How will it differentiate?
No. So one question is, I should stop. So I'll answer that and stop. One question is, I have, there is a piece of memory where I'm incrementally building this data, okay? And whenever you say, no, not commit. Whenever you say, send something with this data type, I go and provide this piece of information to there so that it can be interpreted. But it's not going to be interpreted now. It's going to be interpreted at wherever it gets used, right? Many times. And so in order for that to become efficient, it's probably going to have a compact way to store all the pieces of types that it has, right? And one invisible to the user area of memory, right? So now when you say you say I'm going to add one more field, it's going to keep allocating space so that it can keep adding these new pieces of information. Now that it knows it is this big, this type definition is this big, it can figure out how much space this is going to take. In the meantime, you're building some other type also. Right? So you're building many types, and whenever a type gets committed, it's going to be snapshotted over here. Right? That's a guess, but that seems logical to me. All right, so let me stop here, and we'll spend some more time. I was hoping to finish MPI today. Okay, so are there any other questions on the type? Okay. Now, admittedly, those questions are not particularly important. And there may be a variety of reasons why commit is needed. Doesn't make much difference to the programming paradigm, programming style, learning to program, and all that business. In MPI reduce, will provide the array which gets reduced, an array where the reduced result is going to go, and how many things are getting reduced. The count tells you how many, so you can reduce multiple things at the same time. And something that is of type MPI operation. Okay. The predefined operations like MPI sum, MPI multiply, XOR, and stuff of that sort. You can also create your own. You can write a function and register it as a type. So whenever it sees that type, it essentially becomes a function pointer. And if you do MPI all reduce,
multiple elements, if they get reduced, they'll be operated by the same operator.
yes, yeah, there is no array of operators that's being provided. And as it says, you cannot provide the same variable in the result as well as the input part. Okay. However, there is an MPI in place constant also. So instead of the data array, you simply say MPI in place and put your result in the result array, and everybody else's result is going to get combined into the result array. Okay. And there are MPI all reduce is similar to MPI all gather. By the way, MPI all to all is what I had mentioned. All to all is not broadcast of everything to everybody. All to all was correct in that diagram that I had shown you. There's a reduce scatter, which is reduce followed by a scatter. And then if there's also a quick example for how you can create your own function. You write a function and you create an op, giving this function as a pointer. Okay. And later on you can free that op. There is a scan, which we had discussed, right? It's the prefix sum. Again, not just sum, you can say any operation, which you can again create. And there is an MPI e-scan for exclusive scan, where the elements before you, strictly before you, are reduced to get your result. And in MPI scan, elements before you, including you, it's the inclusive scan, are reduced to get your result.
And it's like it will the rank to figure out who the element is.
The rank, yes. Okay, here's an example. In this case, it is in place. So you can see how in place is called at the bottom. Instead of send buff, it's just sending MPI in place. Receive buff is where the data is going to go. And it says I'm going to do 5 elements, scanning of 5 elements. Each is of type int, and the operation is sum. So it's prefix sum. And this is for my entire group, which if it contains 4 processors as shown in this, or threads, shown in this example. Then receive buff in the beginning, everywhere will be what is on the left hand side, and receive buff at the end, everywhere will be what is on the right hand side. Oh wait, not everywhere.
So leave the last part.
No. Yeah, no, sorry. It is everywhere, right? Because prefix sum is up to you. So everybody has to get the result of up to you.
The P2 is the processor.
Yeah, so P's are processors. So P1 in its first position gets the sum of its first value and P0's first value. Right? So if you see so each column is being reduced, scanned. And so the first column, which started off as 3, 5, 2, and 1, has turned into 3, 3 plus 5, 3 plus 5 plus 2, 3 plus 5 plus 2 plus 1. Right? And similarly, every other column.
It sums like 8 plus 2, not 3 plus 5 plus 2.
Where are you?
From P1 to P2.
Yeah.
Adds 8 plus 2, not 3 plus 5 plus 2.
Let's talk about that. That's one of the important algorithms in parallel, or basic algorithms in or basic parallel algorithms that we do need to discuss in more detail, because it's instructive and illustrative. Okay. There are also, so we've talked about the basic communication operations so far. There are also a higher level process management operation, right? So you could say that MPI run at 5 places and it's going to create 5 of them. But what if you later decide that you need more? You can create more. Okay, so you can MPI spawn processes. When you create a set of processes from one of the threads, so when I say threads, we actually don't mean Unix or POSIX threads. It means one unit of execution. So you can spawn multiple threads from a single thread, and those threads that you spawn will get, when they say MPI world, they'll mean that group. Okay, so the MPI world doesn't include everybody. You have to create that communicator. And in fact, this may be a good time to point out that there are 2 types of communicator. One is called intra-communicator, one is called inter-communicator. Intra-communicator is basically what we have been discussing so far. We have a group and everybody is doing operations within this group. Okay. Inter-communicator has 2 groups. It communicates from one group to another, and then the group communications still are defined for that, but the semantics is slightly different, right? So when you broadcast, inter-communicator broadcast means group is in one of the root is in one of the groups, and the other group, every member is a recipient. Okay. Similarly for gather and scatter also, the semantics are slightly different. There is also a feature in MPI to think of remote memory as shared memory. This tends to be extremely inefficient, but you can create a memory-like operation on remote machines. So there is something called window with type MPI win, and every thread can create a window. Window means it's creating a window into its own local memory, and through that window, other threads can access this thread's local memory. Okay.
That window is shared.
That window is shared, right? So when you can say that I am going to, you see how this is created. You declare something of type window, and you create, and everybody in this world is probably creating its own. You say base memory, some pointer. This is how many I am trying to generate. Info says something about permissions and how to access this memory. The disp unit is, if I recall, similar to the memory type size, the MPI type size, right? Where you used to say 100 ints rather than saying how many bytes. Okay, so it's basically saying that I've got base memory is over here. It is so many of this type. I think it may have to do with slight generalization on top of MPI types, so that you can simply say that my types are this size, this big. So when you want to access something from my memory, you have to tell me how many elements you want from which location, and I'm going to multiply by disk unit to get to that position. Okay. So instead of you giving me precise offsets, you're giving me offsets in some unit size. Okay. That unit size may be the size of an MPI data type or may not. Which is a generalization on top of this. And this is something that everybody has to call. So that window, when you get your own window variable, you've got through that window variable an access into all the remote locations. Okay. So now you can simply say write into somebody's. That window will tell you, or through that window you will say write into this window that rank ID, that piece of information. Okay. So let me here MPI put is how you would write into somebody else's data. And in fact, yeah, I see here it is display unit times display size, which is precisely what I was saying. There's source address and source count, which says from here, write from here, so many things of this type to that destination rank in my group. Destination display. Is it display or something else? I'll have to take a look. Displacement, yes, that would make sense. Destination displacement, the count, how many on the destination side, and a destination data type. Right? I'm writing ints so many units away from the base memory, base offset, on that window, that rank. Right? So that because everybody had called with the same window earlier, right? MPI alloc mem, system is able to figure out which address of which processor are you talking about. Okay. There's also an MPI get where you can read from another processor's memory, another thread's memory. There's also an MPI accumulate, which is similar to MPI reduce. And so, except it's one-to-one. So you can say that you can write something into a destination memory. You can say add this value I have into that guy's memory. So instead of read and write, which you can expect will be more expensive, you simply send it one way, saying I'm sending it to you, perform an operation and write it.
You can get need to match.
Sorry?
You can get need to match.
No, there is no matching here.
It's shared memory, so
Yeah.
that thread does not know that I am writing.
Yes, yes. Now, if you want that thread to know, that's programmer's business.
So in the last slide, when you created the shared memory, then that was creating the shared memory on me, which is shareable to everyone.
Yes, and everybody was doing that. Right? Everybody was making this call, MPI win create. And everybody got, in response, a handle win. Okay?
Which will have addresses of shared memory for everyone.
Implementation details can vary.
No, so what I want to ask is that whether doing this in all the threads, shared memory in each of the thread, which is accessible to each of the threads.
Yes, exactly. And through your local variable called win, right? That has enough information to which it was matched.
And the shared memory model is NUMA.
Very NUMA.
Because it gives the number of
Right.
rank.
Right.
Yeah, what is the memory consistency model?
Memory consistency model is not well defined for this. So the standard does not specify. Right. We can figure out what OpenMPI does. I suspect it is weak consistency model. It may also be something called release consistency, which is similar to weak consistency, but a little easier to implement. There are also variety of synchronizations because, as I said, programmer must make sure that if I write something there and that process needs to know that I have modified that value, I need to be able to synchronize between the two of them.
So these lock would be within the communicator, global to the communicator.
The lock would be within the communicator for a specific memory item, right? So that we can synchronize. It's like shared memory, right? But I want to lock this memory so that nobody else can read until I have updated it or something of that sort. So you're locking a specific shared memory item. Fence is similar to barrier. It says that I have done some shared memory operations, MPI puts, and I do a fence and then do an MPI get. That means my put has been, everything before the fence has been completed.
Like flush.
Yes, it is very like flush. Okay. Anyway, there are a lot more details. You can look it up. There is a little bit more to MPI too. There is synchronization between their relative reads and writes. Right? Default read write says what? When I print something, the standard out goes to the master, whoever started it. Standard int becomes null. That's a very unsatisfactory model for many situations. Moreover, for file I/O, when I am also reading the same file, which may be shared using NFS or whatever, and the other thread is also reading the same file, we need to be able to synchronize in some way. So either we can lock something or just the file operations, just like memory operations can be synchronized, can be individually synchronized. So that can be done. There's also socket style direct communication. If you want something more general than what is being provided, then you can open stuff. Okay. That's as much as MPI we are going to talk about.
So is MPI really, I mean, it looks scary when you go through all this, but I mean, is it really used in practice?
MPI is the widest used multi-computer because it has so many things, and those two are related, right? This is an open source product. Why does it have so many things? Because so many people are building it and so many other people need it. Right? So that's the thing with open source. If there is enough interest, then it gets done.
They kept on adding features as
Yeah, right. So MPI 1 didn't have any process. It was basically a communicator, send and receive. And then all these meta level features started to get added. That's one of the reasons why MPI was not a clear winner at MPI 1 stage, because it didn't have a way for you to program multiple things. It only had a way for you to tell somebody else to do something. Right? Now you can actually say, create this process, run them in parallel, produce the result, reduce the result, and done. Okay. And so it now, although not everything is as efficient as it could be, feature-wise, it can actually help you do a lot of things. So for shared memory, OpenMP is by far the methodology of choice, although there are competitors which are similar in nature in many ways. And for distributed computers, OpenMP is the methodology of choice. Okay. All right. So we'll stop here. We'll start talking about algorithms, and one of the first we'll talk about is the scan, prefix sum.